So hello everyone and welcome to our next session of our Digital We Days. So I'm very happy to welcome all of you and that you took the time to participate in our today's session with the topic Diagnostics on PCB. I'm also very happy to welcome Arnaud Wendling and so he will do the presentation today and also answer your questions. So then just some information from my side at the beginning. You will be muted during this webinar. That means that you cannot ask us your questions via your microphone, but you can always ask them in the chat with the chat function. And then after the presentation, we have the time in the live Q&A and we go through them. So also if you have any questions about the handout, we will share the slides at the end. And also we will share the link to the recording in the next few days. And if you have any other questions left, then just email us at digital-v-days@we-online.com. So, okay, enough from my side. I wish you an exciting webinar. Arnaud, the stage is yours and have fun.
Yeah, thank you, Markus. So good morning to all our attendees on this webinar. I am Arnaud Wendling, Product Manager for Controllers at Würth Elektronik ICS. So let me introduce the topic of today as soon as my screen is shared. Yeah, here we go. So welcome to this topic. We have today, we are here to discover the different diagnostic possibilities we can offer onto our power board and customer-specific solution. First, I will start with a definition of what we do understand about the system diagnostic and what could a solution like this offer to your customers. Then the main part of the presentation will be to present you the many solutions we can equip on our power distribution board based on PCB and press-fit technology. The third part will be a bit of advertisement. I promise to keep it short. Our goal is to build a system for you, with you, and for this, I will introduce the services we offer to our customers. We have organized our expert network to be able to cover a wide spread of customers' requests and to always bring together the needed skills. Finally, we will close this presentation with the usual Q&A, question and answers, where we will have a chance to get a direct answer to your integration. So let's get started, shall we? Würth Elektronik ICS is focused to offer customer-specific power distribution systems in low and high voltage area, HMI solution and controllers. But we do offer as well PCB components to allow you to design your own products to profit of our well-known power elements design. When we speak about diagnostic on PCB, there is, of course, a PCB involved, which means we are really addressing our core business, the electrical central unit. The distribution of power in your vehicle, and here we have a solution from the data acquisition till the user information. But what do we understand about the diagnostic of a system? Indeed, it is all about the function of each part of the vehicle, each load which is driven. And this is where the questions are. Is the load powered? Is my system ready to power my load? How is the health of my system? Is my fuse blown? Is my load okay? So many questions and much more actually. We won't speak too much about the preventive maintenance or any highly communicative aspect today. But the fact of being able to get a diagnostic, a status of the electrical system, of the load attached or driven from an electrical central unit is the starting point of a wide array of possibilities. There are some direct ways visible onto the PCB directly, or the diagnostic can be gained through the dedicated hardware, a controller, which is in charge of handling the logic and responsible to communicate the aggregated status of the system to an HMI or telematic solution over Canvas, for example. Let's discuss shortly about the physical parameter which we are of interest for a PCB solution. On all, and that's not a light word, all our PCB solution, there is one element which is meant to fail, to be the weakest link in the powering scheme, the fuse. The monitoring of the fuses is a pretty critical information. Not only is it important for the system, but as well to the end user of the machine. It has to be quickly and easily confirmed that the powering issue comes from a blown fuse. Then the temperature. This is as well an important parameter. Why? Very easy to explain. The temperature is a limiting factor for many components, starting with the relays. They look very powerful, but let them exceed the room temperature and the performance do decline quite rapidly. And for us, especially, the PCB design with its track width, thus temperature elevation generated by current flow is quite critical too. A surveillance in some critical cases can widely help to prevent things that no one will see too hot. Then current is the next parameter we want to be aware of. There is only so much current available in your vehicle that the generator can create and the wiring harness can transfer. So many things can be done with the current monitoring, especially in preventive maintenance. But for us, this is mainly the status of the current flow, which will define the main characteristic. The current reading method can be in line or with the help of non-intrusive sensors, depending on isolation is requested or not. And last but not least, the voltage. If too low, nothing works. If too high, something is definitely wrong and the system should be protected. Its presence or absence is sometimes good, sometimes bad, but it is as well the main channel for sensor to communicate with the controller. Of course, all those physical values need to be read, acquired, and processed through a controller. For fuses, the status needs to be trigger an alarm. For temperature, it can trigger an offloading or an increase of airflow to cool the system down. For current, we can detect an open load, a default in the wiring harness, or a short to a potential. The voltage can give many information, but it needs to be evaluated to be meaningful, especially when speaking about a battery management system, for example, which takes all in account, all those parameters together to evaluate the state of the health of a battery. A controller does mainly two things. At this stage, it reads and reacts on one side, and it communicates and informs on the other side. And what is better than a vehicle able to directly inform with text and images the end user, or give clear diagnostic to the maintenance services to ease and accelerate the reparation process. The diagnostic of a controller takes many aspects. Many protocols have been defined to provide a system with a standardized way to communicate. So, first part finished. Now I propose that we dig together into the main part and discover the many ways we can provide diagnostics on our PCBs and for your projects. What we will review today are the following aspects: the fuse diagnostic, the temperature of the board, and how to evaluate it. Then the current flow, or better said, which solution we can offer to measure the current load. And finally, the voltage measurement, which will take place on our controllers. All those parameters can be measured, acquired, and varied in many ways. Let's start with the fuses. This component is the weakest link in your electrical architecture, and this by design. Fuses are coming in many shapes and power ranges. At this point, I would like to remind the rating selection guideline we use in our design. All fuses shall be used at 70 to 80% of its nominal value. If we take some seconds to set the context, somewhere in your vehicle, a fuse did just blow. Many reasons could have caused this issue. But fact is, you need to replace it to get your machine back on track. And first task, after finding out where this weird fuse board is located, is to find which one of those fuses has blown. For this, a first help for it on our PCB is the fuse tester. This is really an easy thing to integrate on any PCB. The principle is quite easy. Present a fuse to the two terminals, and they are compatible with shapes from mini fuse to maxi fuse. And if the fuse is okay, the LED will light. If the fuse is blown, nothing happens. Of course, you could say that this with transparent fuses, like on this picture, is quite easy to see. Yes, that's true, but that's not the case for all fuses. Another option that we are well equipping many of our customers' board is to have a fuse test located on each fuse of the board with a button to activate the LED. Nothing fancy here, just switch the LEDs to the ground. Once activated, all the fuses which are OK and powered will light, and you will easily see the blown fuse without any manipulation at all, other than the push of a button. Upon request, this button can be either a switch, toggle, or momentary, or a push button. Another solution will be to get rid of this button and simply connect the LEDs to ground. There is then always a power indicator on every fuse. When I say every, I mean, of course, the one which are required to continuously show their status. This solution has a huge drawback. The current will be drawn in all cases, and if one LED is not much, the addition of many will have an impact on the global idle mode consumption. We have a variant available as well, where the blown fuse can be shown in red color when blown. In that case, the green LED can be an option which can be removed to save on idle current. That was the easy way, which requires a physical access to the board to achieve a diagnostic. We can as well implement a controller to survey the whole system. And this is mainly the reason behind our pluggable controller product range, the ICCS CAN controllers, as well as our new product platform, the power distribution CAN controllers. And of course, when we speak about controllers, we speak programming. For our current product portfolio, we are using our in-house ICCS SDK Plus. And for our new platform, we are using our WE Control Designer, which is based on the PLC programming, offering the combination of several programming languages. In all cases, the application fuse test is quite simple, as we are reading the status of the fuse with either an analog or digital input. Once this information has been acquired, it's up to the programming to decide what to do next. But the common way to handle it is to inform the driver through a human-machine interface or in another visual way. Here, without all the detail, I just made a snapshot from our programming environment to demonstrate how easy it would be to construct a CAN frame with the status of many fuses in it and send it over CAN bus as a monitoring application. Now I would like to catch your attention to some different approaches that we can implement for our customers, depending on the diagnostic goal. So if we take the same schematic, a classical fuse and relay structure, the question is where to acquire the information and what does it mean for the system. On this first example, the status will be read between the fuses and the relay. This allows a constant diagnostics of the fuse status and to know if the fuse is okay at any time. On this second example, the acquisition will be made on the relay's output, which will allow a diagnostic of the power delivery capability, which is only possible when the relay is activated. On this last example, we will use two inputs of a controller to have a complete status of the output stage. This allows us to validate the fuse as well as the relay. If, for example, the relay is not switched on through the controller's output, the relay could be defective. In the same manner, if, when turned off, the input after the relay is not losing its potential, the relay could be stuck. Going one step further, if the input after the relay gets powered, we could even detect a short to bat on the wiring harness to prevent the output to be activated at all. The next topic will be the temperature measurement into our system. The temperature is a main limitation factor for many components and a daily fight for our customers. When it comes to temperature, the hotspot localization is one topic. Of course, we have guidelines in the layout and PCB design, which will widely help our system to handle power without too much heat generation. But when the components are heating on their own, this is a whole other challenge. The context of the temperature measurement is as well a little bit peculiar, as the temperature sensor is giving out its own temperature, not the temperature. The position of the sensor makes a huge difference depending on if you want to know the inside temperature of an enclosure or a track temperature on a PCB. For this purpose, we are offering new temperature simulation services to our customer to allow a better design from the start. The first type of the sensors will be the well-known NTC type. This cost-effective solution can be easily implemented and comes in many types and shapes to match different use cases. The temperature range of these sensors is compatible with the temperature range that our products have to endure, and is therewith a good choice. This kind of sensor is then a little bit tricky to read and to handle. There should be a controller reading it, and there is a need of an adaptation circuitry to handle the very low current which is required here. Indeed, we don't want the current flowing through the NTC to elevate the temperature of the NTC itself. We want the NTC's temperature to represent the surrounding temperature. Some of our controllers have special inputs with operation amplifier, or so to say, infinite impedance, which allows such kind of readings. And of course, the final goal of this reading is to provide the information to the user, to the system, or to the telematics, whatever is used to make decision about this value. One other challenge with those NTC is that the response impedance to temperature is not linear. Therewith, we need to calculate such conversion within our programming, allowing to directly offer a temperature in Celsius degree to our system. Another type of sensor for temperature can be an analog device TMP series. This kind of sensor is an active IC which requires a power supply of 5 volts and is relatively stable or slow in temperature measurement. This is a good choice when the temperature changes are not rapid. Cost-wise, they are only a few cents more expensive than an NTC solution, so more or less equivalent on a global functions cost. The advantage of this IC is that the voltage coming out, which represents the temperature, is not impacted by the impedance of the analog input indeed to read it, and is linear, which allows an easier implementation in the system. Still speaking about temperature, and now directly act in case of too high temperatures, and without additional controller, we can as well implement thermal contacts. Those components can be seen as a thermal fuse, which will rearm automatically. They will open when temperature rises above a defined threshold, and close when temperature has lowered for at least 20 to 30 degrees Celsius. They are capable of switching up to 1 amp, and depending on the voltage, offer between 30,000 and 100,000 cycles. To read the status of those thermal switches, it would be identical to the regular fuses, simply by using a digital input on a controller. We have now viewed the fuse status and the temperature. Let's have a look on the solution we offer to get knowledge of the current flow in the vehicle. The global scope around current measurement is very wide. You may want to know the overall current consumption of the current flow of one specific output. Maybe a rough idea is enough. Maybe you need something much more precise. There are as many use cases as there are systems and loads. And the real question still is, how much current do I draw from my battery? Current monitoring is not limited to our, I would say, low voltage 12 and 24 volt systems. These requirements apply as well on the higher voltage system, 96 to 800 volt, where there is a real safety and security aspect to it. In the next slides, we have added a small information about voltage area level, and if it's valid for high or low or both solution, just to get you a better understanding. In this part of the webinar, we will see mainly two types of current measurements. First, the built-in current measurement offered through the SmartFET technology and embedded in our controllers. Second type will be the external current measurement, usually realized through additional ICs on the PCB, which are capable of measuring much higher current values from 15 ampere up to 800 or more. If we take one of our last product, for example, the CANbox 8FR6, this controller has both technologies implemented. On the high side output, we are using the embedded current measurement, a possibility offered by the 2-amp SmartFET output stage. For the relay, we are measuring current up to 15 amps by the use of an external current measurement IC. This feature, in addition with the other diagnostic possibilities of the controller, is always oriented to offer the maximum awareness to the system of its own status. In the programming environment, we have implemented some special blocks where we can define the expected current, and then those blocks will directly return error codes like open load when no current flow is detected upon activation, or overcurrent if the nominal value is too far exceeded. We are also offering current measurement in somehow simpler modules, like our solid-state relays, which are devices on a mini eiSos relay shape, so pluggable into our sockets. With a range from 5 to 25 ampere, those relays are returning a voltage proportional to the current passing through them. Here again, we are using the SmartFET technology, which allows them to be protected against short to bat or short to ground. To evaluate the current, those SSR can be used in combination with a controller to measure the value and provide the diagnostic to the system. Okay, let's turn to some components which could be used on power board directly. We will speak about the Hall sensors. Those current sensors are able to measure current in different ways. There are many implementations, but mainly two types of sensors, which are called inline, where the current needs to pass through the components to be measured, and the sensors which are non-intrusive and are measuring the current passing through a conductor. Typically the same principle that you will find on a current clamp. Whatever the sensor type, those are active sensors, which needs to be supplied and are returning a voltage or current image proportional to the current being measured. Here again, we need an acquisition system, naming a controller, to read, process, and communicate the information to the system. Interesting is that those non-intrusive sensors can be used in higher voltage as well. To give you some current rating indication on projects which we have realized in the past, we have worked mainly with Allegro's and LM sensor. The Allegro with the big ears is a THT component that can handle current up to 100 or 150 ampere. The SMD version of this sensor has a limited amount of current, up to 15 amp, but it exists 10 or 25 amp versions for lower needs and higher precision. The LM sensor we are using is the HTFS series. This one exists in 200, 400, and 600 amp range. Here we have a nice combination to offer by using our power elements and the round sensor, which can then be located around it. This is really useful for our customers, especially during the prototype phase, where they can make all the validation of the current flowing through their PCB. And when everything has been set up and validated, the decision is taken that the sensor is no more needed. We can simply unpopulate it and making no modification on layout or on the performance of the board. We have other solution as well. Shunt is a possible solution, whereas not the most used on our side, as it requires quite some additional component on the PCB for the evaluation of the delta voltage over the shunt. Another solution we have implemented is to make a partial measurement. When the current is really too high, we can use a sensor and cut a bus bar in a way that the current distribution is defined upfront, making the total current proportional to the measured current. Not the most precise current measurement, but good enough for the amount we are speaking of, several hundreds of amperes. And here you have an example of our demo box for CDM A16 module, which stands for Control and Diagnostic Module, especially tuned to read the fuser status, supply and acquire some sensor on the main board, and control the relay with pick and hold function to reduce its generation. On this board, we will offer 3 different current sensors. The most obvious is a huge LEM sensor, which is directly connected to the main fuse on the box, 2 different ways to read temperature, and many other diagnostic possibilities, along with an effective 150 ampere power distribution capability. Having a current measurement on the main power entry is only a first step. You can use it as a bulk value, or you can make some more analysis in the software. For example, you can assume the current draw from different outputs by simply making a measurement before activation and a second one shortly after. This will allow you to have a limited but somehow good idea of the current draw from each output. This reduces the need of many smaller sensors, and at the end, a single, a bit more expensive, could be more cost-effective and still enough. Let's head to the last type of parameter to be read. We have already discussed about it with the processing of the current sensor, but voltage measurement is as well a good indicator of the health of your system. If we take our pluggable module, the 64PV2, presented here on the picture, this module offers a wide spread of analog or digital inputs, which can be used to read different signals in the vehicle. Digital inputs are used to detect presence of voltage, perfectly adapted for fuse surveillance. We would have 7 analog inputs rated 0 to 10 volt and over 20 digital inputs. 3 analog inputs with 0 to 32 volt rating, and 4 analog inputs with operation amplifier scale from 0 to 5 volt. So extremely high impedance to process temperature sensor like the NTCs or resistive fuel sensors. Here we are providing as well the 5 volt supply, which can be used on the PCB to supply different type of sensors. When we speak about high voltage, where we need as well to offer a voltage measurement, this is a complete challenge of its own, to offer the right amount of isolation and precision. LEM has some solution for that. Rated up to 1000 volts, they assure the needed protection and isolation, but they are quite expensive and still require some control to process the measurement. In terms of diagnostics, for either high or low voltage, there are still many other solutions on the market, like the HELA intelligent battery sensor, which are independent sensors providing both current flow and voltage of the battery, along with many other batteries dedicated to indicators such as temperature, state of health, state of charge. Those sensors are often directly communicating over CAN bus or LIN bus and do not really have their place on our power board. But I wanted to give you a good overview of the diagnostic solution we discussed with our customers. In some cases, we still implement the diagnostic of those sensors directly on our controllers. We are then more speaking about communication diagnostic as with physical values. We diagnose, and if the communication with the sensor is successful or not, and return this diag to the main interface, along with all the other parameters we are watching on our power boards. And we are at the end of the presentation. I still want to say some words about the service that we are offering to our customers, because as you could see during this presentation, there are many answers to a simple question. And with our team, we will always aim to deliver the best answer adapted to your case. To provide you the best service, we have different teams taking care of the different question or problematic you could have. Our project management team is providing the best support to help you discuss your project, understand your needs, and to propose a good solution. You can count on our international experience of so many customers in so many different fields: agricultural, construction equipment, trucks and transportation. You name it, we have a customer in there. For all your software and data processing questions, our field application engineers are here to support. I am pretty confident to say that the sensor you are looking to use has already been implemented in one of our projects. And when the things get hard, our research and development team has experts in many thermal, hardware, or software fields, and of course, access to our sister company, Würth Elektronik eiSos network and support team. So I am again pretty confident about our capability to answer your question and would be happy to receive your challenges. And the last slide, I promise, the takeaway for the day for you. I would like you to remind that the power board, which you know us from, with its quality and power delivering capability, can do more. We can provide more diagnostic to your system than you think, and this could help you in other areas such as maintenance and offloading in case of the over temperature or overcurrent is detected. The first step for solving a problem is to know that you have one, right? We, Würth Elektronik eiSos, are able to support you in the selection of sensors for the 12 and 24 volt, but as well for higher voltage application. We have the team and the understanding of your application. And of course, we are sensible to the costing and aim of use aspect to propose the right solution for your application. So thank you so much for your attention. And I will like to thank you very much for your attendance. And I will now open the question and answer session of this webinar.
Okay, so Arnaud, thank you very much for your presentation. And yeah, so now we have the time for your questions, and I can see there were some questions already coming in. But before we start, I will quickly also share the handout. You should now be able to see it, and you can download it directly. And also, if you miss it now, you can also just download it afterwards. You will get the link from us. So then, Arnaud, let's start with the first question. Where can I find more information about the product range?
So the first help for finding information will be, of course, our website. There are a lot of information, data sheet, and information around the products. Then when it comes to discussing this a little bit more in details, we have support, of course, from our sales team and our field application engineer, which are here to help and support you selecting the right product or right sensor around your needs.
Okay, thank you very much. Then regarding sensor, there were also another question. Are you selling the sensors as well?
No, basically we are not selling the sensors by themselves. We are buying those sensors to implement them on the PCB and then delivering the whole package as a system to our customers. So we are a system provider more than a component provider. This is mainly our main difference with our sister company, eiSos.
Okay, then Arnaud, thank you very much for that answer as well. Then let's go on here with the next question. Are there other interface options than CAN available on your diagnostics controllers or CA?
Yes, we are. So currently on our products, we are offering first CAN bus as a highlight of all the controllers. So there is at least one CAN bus interface on our products. Some have 2 or 3 interfaces if needed to communicate and act as a gateway. We do offer as well controllers which are supporting LIN bus. LIN bus can then directly manage sensors like the ELA battery management system, or some alternators which are LIN communicating to the system. Or as well, we are managing for some customers the rain and light sensors on the windshields, which are as well LIN sensors. There are as well some keypad inside. So that's the main focus. For the new platform we are working on, there will be as well Ethernet connection in the future.
Okay, that's a nice outlook there. Thank you very much. Then let's go on with the next question, Arnaud. I saw during the presentation a current sensor with a bar with current, I don't know how to spell this, divider function. Can you suggest a product number or a series, Arnaud?
Yes, we are using the Allegro sensor for this case. We have now opened a new type of product on our side, which are the bus bar and the custom bus bar definition of creation for our customers. So we are investigating here to have some more information gathered together in the future. This is still a new activity for us in regards of the bus bar because we are more keen to work on PCB, but bus bar is a nice advantage for our PCB to increase locally the power rating of some on some tracks.
Okay, thank you very much. Then let's go on with the next question here. What do I need to start a project?
Well, first of all, you need to have a vehicle. That's the basic one. No, we are working with many of our customers, starting from the schematic from the vehicle, the electrical schematic, cutting that down and looking where we can fit all the components and fuses and relays. And then we introduce our controller, and this is an exchange between the customer and ourselves. And of course, what we would need in that case is some software requirement or behavioral requirements from your side, just to know what your system is supposed to do and how the power board is supposed to react and integrate into the whole system. So starting with this, quite easy, sales contact, schematic, and some space in your vehicle for the power boards and some ideas about what has to happen. And this will be a good start already.
That sounds very good. Okay, Arnaud, so thank you very much. I think that's for now all questions I can see. Maybe there will come more. So if we can't answer it today, or you have some questions open, then just email us. We will be there for you and support you. Also, just the information, you will also get the link to the recording. And then I would say, stay tuned. We also have a lot of other topics coming up for, like now the next session, turning the RF, learn about impedance dynamics. Maybe you're also interested in that one. And so then I also big thank you to you, Arnaud, for your presentation and your time today and all the answers. Thank you very much.
Thank you to all attendees for having taken the time, and thank you, Marcus, for the management.
You're very welcome.
Goodbye to everyone.
Goodbye. Have a good time.
Have a good day.